Hi, everyone, and welcome to our sixth panel in the Future of Information Processing event series. My name is Demetria Lee, and I am part of the German Informatics Society, which is helping IFIP celebrate its 60th anniversary this year by presenting a series of events that will look at what the future may hold for ICT. Our moderator for today is John Meyer. John is a professor emeritus of electrical engineering and computer science at the University of Michigan in the United States. His career of more than 65 years of research and teaching has been devoted to the design and model-based evaluation of highly dependable computer communication systems for critical applications. These include telemetry and control systems for aircraft and spacecraft, air and ground defense systems, telecommunication networks, and intelligent transportation systems. Within IFIP, he's a founding member of Working Group 10.4, a Silver Core awardee, and an inaugural recipient of the Jean-Claude Lepre Award in Dependable Computing. And with this, I would like to hand moderation over to him.
Thank you, Demetria, for the introduction and for all the effort that you and Christine have made in coordinating today's panel. And thanks also to IFIP for its support in hosting the 60th anniversary panel event series. And a good day to all of you participants out there from early in the morning on the west coast of the Americas to very late in the evening in the Far East. Your attendance is truly appreciated, especially those in those time zone extremes. Let me share the screen here. This is the title of our panel. It's been advertised. Although both safety and security are important concerns at all levels of vehicle automation, safety is paramount. Over 1.35 million people lose their lives each day to roadway traffic accidents. And autonomous vehicles have the potential to reduce this carnage by orders of magnitude by leveraging breakthrough advancements in targeted areas of information and communication technology. However, as we're going to emphasize also in this panel, this must be coupled with governance and regulation that's able to enforce adherence to strict safety standards. Our distinguished panels to address these needs, these four people have diverse expertise. I hit a back button in road vehicle autonomy, but with a common concern for safety. I'll introduce them more graciously as they present their opening remarks. First, a little background. This panel was organized by members of the Intelligent Vehicle Dependability and Security Project of IFIP, Working Group 10.4 on Dependable Computing and Fault Tolerance. The co-organizers, Homa, Jay, and Chuck, have been working from the time the proposal was made and have been extremely helpful with many details, including publicity. And I think in the latter case, it's evident that the publicity worked by the number of participants I'm seeing. Just a note about the IVDS project. It's had various activities since its initiation. And why is this working group concerned with autonomous vehicle safety and security? Since its founding, it's been engaged in identifying and integrating methods for achieving highly dependable computer systems and networks. This includes all aspects of the system's evolution from specification through deployment, and many of these applications have involved safety critical autonomy. Realization of dependable and especially safe intelligent autonomous road vehicles is therefore well suited to experience within this group, precipitating the IVDS project. Generally, this is an information processing imperative for a myriad of information and communication technology disciplines under the IFIP umbrella. And I think this is evident from the attendance at today's panel. Conduct of the panel, the remaining time will be evenly divided roughly between opening remarks by the panelists, a moderated discussion among panelists, followed by a poll of the audience, and then Q&A between audience and panel members. Throughout the session, please use the webinar's Q&A to ask questions, and please address each question to a particular panelist. Addressing it to the whole panel tends to lead to repetitive answers, and we only have a limited time for a lot of attendees. And then selected questions will be answered during the Q&A. And at the end of the session, you'll be invited to continue your participation via a Slack channel and a mailing list, and I'll give you details on that later. And now the panel. Our first panelist is Dr. Philip Koopman. He's a professor in the Department of Electrical and Computer Engineering at Carnegie Mellon. Phil has an enviable resume of work concerning automotive safety and autonomy that dates back to the mid-90s, 1990s, sorry. Currently, he's actively involved with autonomous vehicle safety policy and standardization. In particular, he was the principal contributor to ANSI Underwriter Laboratories 3600 standard for autonomous system safety that was issued last year. Phil also has extensive experience in software safety and software quality across numerous transportation, industrial, and defense application domains. Phil, our pleasure.
Thanks, John. Thanks, John. Happy to be here. Thanks for inviting me to the organizing committee. I'm going to try and keep this brief, but I have a couple main things on my mind these days about automated vehicle safety. The first one is that when you have an automated vehicle, there's no human driver. That's kind of the point, right? Is to get rid of the human. That's the idea here. But there are a lot of implications, especially for the fault tolerance, reliability, safety communities, because it used to be that the person, sure, everyone blames people for being bad drivers. That's kind of an overstatement. They're not really as bad as they're made out to be, although, of course, there's room for improvement. But the other part people don't talk about is that the human is an amazing fault mitigator. So right now you have a vehicle that has all sorts of internal faults and all the weird stuff that happens in the outside world. And that's on the human's lap. The human has to deal with it. Well, when you get rid of the human, now it's all on the car. And so the car not only has to clean up all the external problems, the weird stuff, the did you think of that kind of surprises I like to show on social media, but also the car has to deal with its own internal faults too. And there's no human to blame. So beware of the moral comfort zone. That's the idea that the human is there as the last vestige of driver authority, but the real purpose is to have someone to blame. So the awkward middle of the so-called level 2+, which isn't really a thing, is really making sure there's a driver around to blame if something goes wrong. But if you want this technology to really succeed as fully automated, there's getting it to drive, but the even harder part is cleaning up all the loose ends, all the failures, all those sorts of issues without a driver being responsible for the thing they're not good at, which is watching something boring to wait to see when it breaks. The second piece is people talk about the trolley problem, and I'm going to set a rule right now. I don't want to talk about the trolley problem in this panel because it's a distraction. But the real thing that matters is deployment governance. If you want an ethical problem to worry about who decides when it's time to put these cars on the road. And the situation you have now is very concerning from this point of view. The companies have huge existential pressure to hit milestones. When you give a company multiple $billion and they promise to deploy by a certain date, and that date comes and they haven't deployed, can you imagine the pressure on the people running that company to deploy, even if they're going to cut some corners to do it? Huge, amazing pressure, because maybe that company goes away. Now, some of the actors in this space are exceptionally thoughtful about this, and they're trying as hard as they can to do the right thing. Others, it's not so clear what's really going on. But the issue is that despite your best intentions, with that kind of pressure, it's hard to stay on the moral high ground. The current AV regulations, so you have regulators. What are regulators supposed to do? They're supposed to push back to make sure things are safe, but the regulators are so far sitting back. You see some action with Tesla from NHTSA, but those are not fully automated vehicles. Those are, the autopilot is a level 2 system where the person's supposed to remain in charge. You don't see a lot of regulation hitting the fully automated vehicle deployments. There are regulations, but the regulations have to do with insurance and whether the driver's is trained properly, but safety, technical safety kind of doesn't really enter into it. There is a safety standard that would be extremely relevant for on-road testing, SAE J3018. That's not about the technology. That's just about whether the safety driver is trained and the operations are done in a safe way. So it's nothing about the internal technology, no constraints there, just you need a safety driver. And yet, other than New York City requiring it recently, none of the other municipalities, none of the other states are requiring it, and the industry has a huge campaign on. You don't hear much about it, but there's a lot of effort going into pushing back to make sure that the regulations don't require standards and the regulations don't require safety. So that's kind of a situation in my mind. That's the big moral dilemma we have to face is, how do we know these things are going to be safe enough to deploy, and who gets to decide? Thanks, John.
Thank you, Phil. Our next speaker is Wilfried Steiner, who is Director of TT Tech Laboratories at the TT Tech Group in Vienna, Austria. Under Wilfried's direction, TT Tech Labs acts as the Center for Strategic Research within the TT Tech Group. By the way, if you're not familiar with this, and likely not, the TT is an acronym for time triggered, a computer synchronization technique first introduced in the early 1970s by Professor Hermann Kopetz at the Technical University of Vienna. A colleague of mine, it seems forever. Wilfried's research concerns the design of algorithms and network protocols. With no further ado, Wilfried, the floor is yours.
Yes, thank you very much for the kind introduction, and also welcome from my side. Thank you very much for the opportunity to talk about the need for a conceptual architecture in autonomous driving systems. So as the title of my introduction implies, I'll be talking about the design aspect. How do we think we can reach this goal of establishing safe and secure autonomous driving? So as we discussed already in the previous talk, autonomous driving is a highly complex task. And I would say it's mostly because the highly dynamic environments that we operate in. So there are so many different objects that a car has to face on the street. That's true for a city setting. It's also true for an urban setting, but it's likely true also for a highway setting. But it's not only that we need to satisfy this driving task, we need to also make sure to make this in a dependable and secure manner. So ultimately, an autonomous driving system is a computer system, and it is quite a sophisticated one. It consists of many, many different components. And some of the components are software, there are chip, there's hardware, there is quite sophisticated networking technology and sophisticated I/O. And all of these components may fail. And all of these components may fail in many different manners. So it is a challenge to understand the effect of each and every of these component failures on a system level effect. We must build such a system in a way that it can tolerate failures of components. It is simply not acceptable that single component failures will result in the total failure of the autonomous driving system. And if you achieve to build such a system, we call the system fail operation. Now, as I said, it's very, very complex to trace a component level failure to a system level failure because simply there are so many components. So what we have to introduce is a sort of abstraction layer. And this abstraction layer is what we call a conceptual architecture. So in a sense, we simply group those portions of the system, of the computer system, into fault containment units, where we say this portion fails as a whole. So for example, you could imagine it's a single ECU, a single control computer in a car would form such a fault containment unit. But then we're not going to drill down any further. We say if a component inside this fault containment unit fails, then we consider the whole fault containment unit to be faulty and to adhere to a specified and well understood failure mode. So the conceptual architecture defines what these fault containment units are. It defines how these fault containment units behave also under failure conditions. It also defines how the fault containment units interact with each other. So this level of abstraction is very practical because now we have really a handle on analyzing the system. And we can, in fact, show already on this architecture level that consists of fault containment units and the interaction, certain system level properties. One of the system level properties that we might want to show is that all of the actuators that control the movement of the car are actually using only safe trajectories. Another system level property might be that all of the actuators work on the same set of trajectories. So we exclude the case that some actuators use some trajectory and some other trajectories use a divergent set of trajectories. So we're looking for this consistency property. So if you have established and shown that the system level properties hold on this abstraction level of FCUs, we can then take advantage of this top level description and derive implementation requirements. And we can actually build a system that satisfies the assumptions that we have taken for the fault containment units. So in summary, I think there is a need for a conceptual architecture because it allows us to reason and prove system level properties. And once we have a conceptual architecture established, we can use that as a blueprint to develop a concrete system. So I'm looking forward to further discussions in the panel. Thank you very much.
Thank you, Wilfried. Our third panelist is Dr. Mary, or better known as Missy Cummings. She's a professor in the Department of Electrical and Computer Engineering at Duke University in the United States. At Duke, Missy's the director of the Humans and Autonomy Laboratory, which focuses on multifaceted interactions of human and computer decision-making in complex systems with embedded autonomy. And Missy has also had hands-on experience with exacting human-machine interaction earlier in her career, where after graduating from the United States Naval Academy, she was a US Naval officer and one of the Navy's first female fighter pilots. That's human machine interaction. Our research interests include the human role in cybersecurity, how humans create, use, and test artificial intelligence, assured autonomy, human systems engineering, and the ethical and social impact of technology. Missy, please.
Thank you, and thank you for having me. So I want to dovetail on the safety issues that we heard Phil talk about, and then Wilfried when he talked about the conceptual architecture issues. You know, I agree with everything that's been said up to now, although this issue of testing gets tricky when we start thinking about artificial intelligence. Prior to the most recent years, when we tested systems, we would consider them deterministic, meaning that every time your car started its engine and drove however many miles in the city or in the on the highway, it generally performed the same way every time. There was no second guessing what the next behavior of the car would be. They would be highly predictable. Unfortunately, because we're starting to embed significant levels of artificial intelligence through machine learning, then we start to introduce a lot of problems. And so I just wanted to, I'm going to take the academic perspective real quick and explain to you that, first of all, artificial intelligence, and I'm specifically talking about connectionist AI today, meaning neural networks. Really, we're talking about what appears to be an objective mathematical approach to image, computer vision, but all the lessons that I'm going to talk about today apply to natural language processing, basically any use of artificial intelligence. Is that indeed it is not objective, it is highly subjective. And not only is it highly subjective, it is also oftentimes guesswork in terms of how the systems perform. So the black box, and most people in the audience have heard about the black box of AI, meaning that for neural net-based AI, when we shove a bunch of data in, we don't really understand how it works. That is true, but there's all different sources of bias to say, okay, we know about data bias, the underlying data, if you pick bad data to use as your models, then you're going to have bad outcomes. Okay, that's pretty well established, and most everyone knows that. But what a lot of people don't realize is there's significant uncertainty in the way that the algorithms are chosen. I often say I will never get into a self-driving car that any of my students have ever driven, because I know what their limitations are in terms of understanding what algorithm should I pick to do, what convolutional neural net should I use, how many layers should I use. We don't really have an established way to pick hyperparameters. We just pick what we pick because it worked for us before. So I think that people don't realize that just in the creation of AI, there's significant uncertainty. And then in the picture you see in this graph, this is a very well-known problem where it's basically the labeling of the data, that when the AI is applied to an image, in this case, and this was a Bosch system, this computer vision system sees 2 cars, 3 bikes, and 1 person, where you just see 2 cars. It's clear to you that it's 2 cars because you leverage inductive reasoning, knowledge-based reasoning, to understand that you're just seeing 2 cars. But because computer vision sees the world from the pixel layer and has to construct a world from the bottom up, it sees all of these different entities. So this is a problem because we don't really understand how to make sure that the computers don't do this. We don't understand how to leverage inductive reasoning. We have that is just off, it's the holy grail right now of AI, is generalized intelligence. We don't know how to do it. We're not even close to doing it. And those are for the people who are building the AI. Then at the very last, we've got people who, in this case, I'm representing the man with the clipboard as a regulator. Like, we're supposed to, National Highway Traffic Safety Administration, Federal Aviation Administration, the Federal Drug Administration, who's doing medical robots, government regulators have very, very few people in their offices who understand AI. And even if they understand AI, just conceptually, they don't really even know how to get into the weeds to figure out, is the AI performing correctly? And what does it mean for a system that can make wrong guesses? How do we test that? What do corner cases look like? And this is something that Phil and I talk about in other avenues. So if we've got what is a black box system, both internally, but also I would say is externally, the way that AI is created is still an unknown area. And so this is why I think that we need to spend a lot more effort on testing and certification, because in this nascent world of artificial intelligence, And we see this on YouTube and on Twitter every day with surprises from Tesla, but it's not just Tesla. We're going to have other cars coming online that are hands-free that are embedding this technology. This idea that the car is going to continue to surprise us as it's leveraging AI, this is going to get worse before it gets better. Thank you.
Thank you, Missy. And finally, the fourth panelist, Dr. Ravi Iyer, professor in departments of electrical and computer engineering and computer science at the University of Illinois at Urbana-Champaign in the United States. In addition to these departmental affiliations, Ravi leads the DEPEND group at Illinois' Coordinated Science Laboratory, which, if you're not familiar with it, has a multidisciplinary focus on systems and software that combine deep measurement-driven analytics, and machine learning across critical application domains. These include healthcare, autonomous vehicles, and other safety-critical applications. And if this doesn't keep him busy enough, he also has joint appointments with the Carle Illinois College of Medicine and is a research affiliate at the Mayo Clinic in the state of Minnesota. Ravi, it's a pleasure to introduce a longtime colleague and friend.
Thank you, John. And the advantage of going last, I think, is my colleagues really have set up the problem very nicely. So perhaps what I'll do is be a little bit more provocative. And, you know, I think Missy said it really nicely that what we don't bring into the AVs, into our artificial intelligence systems, is inductive thinking, how we think, and how we are when we're driving. If you think about it, the good drivers, and as Phil said, many, if not most, are good drivers. But they are strange drivers on the streets. I mean, recently I was coming back from Chicago on this very busy highway out of the city, which is and there were 4 motorcyclists who were doing wheelies. I mean, they were on each of the bikes were on one wheel, and you could see how very quickly the traffic separated. And of course, somebody called the police, and they were stopped. But you see, what we do is constantly identify what we call our risky actors. And we are, in some form or the other, dynamically assessing what is the risk. And this is the thought process. And this happens in quick time. It happens in real time, and it can be individuals, it can be other vehicles. It, of course, can be static and dynamic. But this is what we constantly do. And indeed, our systems today, the systems don't quite do this. We are very good at building systems in vision that are really very good with perception. We are very good in planning. We could be better in all these cases. And we have a very long history of building control systems that are very robust. But when we put it together, and as Phil said so well, you take the driver, and now this system has to work on its own. That's where I think the problems start. And indeed, overall, if we look at the real data on how well the experimental systems do, albeit they have a pilot, they are getting better. From the time when we first started to analyze to now, it has these systems, these vehicles, these are getting better. On the other hand, are they approaching the quality or the safety that human drivers have? I think it's debatable. In our measurements, they're not. Others claim we do exceed it, but we consistently see they are not. So what might be, I don't say what might be a silver bullet, but what might be the key to making such systems a whole lot safer than what they are today? And what I say is, we really need for the system to start thinking, building into it a kind of reasoning that we continually employ and use to identify and mitigate the risks. How do we identify safety critical problems? Can we actually start building those kinds of thinking, those kinds of logic into our systems? The example I gave, in fact, on the video, you can see this vehicle just going in, weaving in and out of traffic, and we have seen this all too often. How do we identify these risky actors and continually assess them? We don't really assess 3 or 10 or whatever football fields away, like Google says in its ads that their cars will be able to do. We actually go and assess things around us. We narrow it down continually to a few set of risky actors. And by actors, I mean both static and dynamic. And then we continually assess them and progressively mitigate those risks. So how do we quantify this? How does the machine quantify it continually and reason about which of the risky situations should it be handling at any time? And how quickly does it need to react? I think those are important questions. Humans react perhaps in half a second, less than a second. Some say between 1 and 2 seconds. But could we really bring it down to less than 100 milliseconds? And that's a number. It's still a number. It could be 50 milliseconds. But how do we build these new kinds of systems? I think that's an important question. Thank you, John.
Thank you, Ravi. I'd like to proceed now with a little further discussion among the panelists and maybe take them in the order of appearance of the opening remarks. And Phil, let me ask the following. How is safety in automated vehicles different than safety in other life-critical systems?
Thanks, John. I think there are a couple dimensions. One dimension is I'm going to say that automated vehicles are harder than a lot of other systems. Even in aviation, unless you're really close to the ground, you have a little more time to deal with things. In natural gas and process flow, the factories there is humming. It's not like a truck tries to run you off the road when you're processing natural gas. So the time constants, as Ravi was talking about, the time constants are really tough. And as Missy was talking about, you have these systems that are not necessarily repeatable, and they're interacting with human players. So it's probably the toughest environment to actually build a fully automated system with all the stuff that goes on. So that's one way they're different. But the other way they're different is all the other industries follow their own safety standards, and the automotive industry has no requirement to follow the safety standards. So you hear about ISO 26262, which is the baseline functional safety standard, and go find a company that says publicly they'll follow it, let alone a government that says they have to. Now, I know that some companies say they follow it, some say they come close, and so on, but go and find some transparency there, that the transparency isn't there. And as I mentioned earlier, J3018 is the standard for safety of road testing that's just about the drivers. And right now in the entire world, the only place I know that requires it is New York City. That just happened. And again, go find a company. Some of them will say, oh, we do something like that, but no one will commit to actually following the industry safety standards. And that's completely different than all the other safety industries. I mean, would you get in a plane where they said, oh yeah, you know, the FAA has standards, but we're smart, we don't need to follow them? I don't think I'd get in that plane, but that's what happens with these cars right now.
Thank you. Any further things to add by other panelists to what Phil just said? Wilfried, got a question for you. And it relates to your opening remarks. Why is it important to consider safety in an early phase of the development of a system rather than later on where you actually can start doing some testing and verification?
Well, I think that safety is a property of the system, and as a property of a system, the car either is safe or acceptably safe or it is not. And if you start with a conceptual architecture, this is the chance that you get things right in terms of safety. You have the chance to develop a top-level view and design guidelines and how to build your system such that you can withstand the failure of individual components. And well, what would be the opposite, or what would be the alternative to not consider it in the starting phase of the design is sometimes later on when you're already done with certain design decisions, and then you have a risk that you find out that certain safety characteristics are not met, and you need to start applying so-called safety band-aids. Well, this is kind of a risky approach because you may find a safety hole there, a safety gap there, and find and design a certain safety band-aid, a certain mechanism that solves an immediate problem. But it's quite a high risk that at the end of the day, you have all the necessary safety measures in place and did not miss any gap in your argumentation.
Thanks. Missy, regarding the several important questions and issues that you discussed in your remarks, is there one that you would like to elaborate on more?
Well, I mean, I can elaborate, but you know, just in the spirit of causing trouble, I'm going to start arguing with Ravi right away. Not really arguing, but so the question came up about what are the right reaction times, and so we know for a fact that this is hard science, this notion of neuromuscular lag. So there is about a half second programmed into humans, and this is basic physics, from the time that an event happens, that the light hits your eye, the signal is communicated to your brain figures out, even for a very basic, like something appears in front of your car, getting your foot to the brake. I mean, at best, the best that you can hope for is a half second. So when you say, can we get human reaction down to 1/10 of a second or 2/10? No, we cannot do this. Indeed, this is why nuclear reactors have automated fail-safes in them to insert the rods if the reactor is ever going critical, because humans cannot be relied upon to react in time to make that safe state happen. So if we know that there's the floor to human safeness is a half a second, and we know that a lot of really bad things can happen in cars between an event and a half second. I mean, that in a half second is, you know, in aviation, as Phil said, that's not a big deal, right? You're not going to hit anything in a half second, but in the automotive world, you're definitely going to hit something in a half second. So I think it's really important that we realize there is a hard limitation here. We are not going to get around that. And indeed, that half second is likely going to get much worse, because you know, and again, I don't want to pick on Tesla because I think we also have a big wave of problems coming with the emergence of hands-free driving, because hands-free driving communicates to humans mind-free driving. Is that the instant people think that the automation is pretty good, then humans typically, they'll check out, even if they're not distracted on their phones, even if they're not touching anything, discussing something in with other people in the car. If you think the automation is pretty good, you will at least zone out in your head. You will go internal into your own mind, do your checklist for the day, think about the argument that you just had with your partner, think about planning, you know, what am I going to eat when I get home, right? So we know that that is going to get worse the more autonomy people are given. So if we can't jump straight to self-driving cars where we know humans don't have to be involved, I would say that I think we are actually in the most difficult, dangerous period of time right now, because we're putting enough autonomy in people's hands that makes it appear as if it's good. And that's just enough time for us to mentally check out. And given our half-second neuromuscular lag, we're just not going to be able to respond when we need to.
Ravi?
Yeah, I think I don't have any argument with Missy on this. I think the half-second rule, I won't quibble with at all. I think it's a good rule. On the other hand, and many actually current planners work at that half-second level. On the other hand, if one has to meet, you know, what you described, Missy, as hands-free means mind-free. I can tell you, people are worried about it. I was telling my mother a few years ago, and now she is 90 plus, but then she was still, you know, she used to think that she could drive, although she had stopped driving. And I would tell her what I do. And she said, look, when is this car going to be available? And how much is it going to cost? And I said, look, it's probably be available in a couple of years, maybe 2 or 3 years. She said, well, you know, your computers continue to fail. That's why you're in business. How do I know that when I turn on the ignition, this car is going to start? Or it won't take me halfway to my sister's house and just give up. These are things that people do worry about. And unless the vehicle can truly exceed and better the half-a-second timeline that the neuromuscular system allows you to do, it's going to be very difficult for it to be truly safe, as you know, the way in which Phil and company go and evaluate the safety and are really putting this into practice. I think completely agree with Missy on this.
I may be confused. I thought the less than 100 milliseconds was referring to what automation was doing and not people.
Yes. That's why I think we have to be so much better than what the humans can do, because the human is out. And I think Missy said it well. It's hands-free is almost definitely going to be mind-free. It's as good as sitting at the back.
Yes, and I didn't mean to insinuate that you said that, but the idea is that automation, if that's the threshold that automation must, you know, that you're going to expect it to perform, then if you've got the 0.1 to 0.5 second gap and you think that the humans are going to intervene between that gap, they are not going to.
I agree.
If I can jump in, the moral hazard here is building a car that is only stable if you can do 100 millisecond control and then blaming the driver for whatever bad happens. That's what I worry about.
But Phil, in this context, there is no driver. I'm sitting at the back, so to speak.
Ravi, in practice, there's no driver. But if the user manual says the driver is responsible and you click through the screen, that's where you get into trouble. I'm in violent agreement with both of you.
Yeah.
Well, we're talking about different levels here of automation, and depending where you are, and I think in the middle, where you're depending on the driver to respond when autonomy makes a mistake, that's where I think Missy's concerns are, and much of her testing work and her other work at Duke, and a lot of us here are concerned about. There's a lot of questions that are being raised in this discussion. Yeah, and clearly we don't have time to discuss solutions, but their solutions have to be made, and that is the imperative that really motivated organization of this panel. Although we might have begin another round of questioning, I really think it's time to get the audience more involved. Let me share the screen here. To get more of you involved in prior to the Q&A, we'd like to conduct a poll concerning the use of safety-related functions. And these are below what we've been talking about, but they certainly are part of the evolution to more fully automated driving. And these are called Advanced Driving Assistance Systems, or ADAS for short. Such functions include adaptive cruise control, lane keeping assistance, automatic emergency braking, blind spot warning, and on and on. However, we're not talking about ADAS functions that are conveniences, such as automated parallel parking. These are not being questioned. So, Demetria, could you please post the poll to the audience?
Yes, I've just done so.
Okay, will this remain on the screen if I continue?
Yes.
It will? Okay, fine. Okay, let's get to questions and answers from the audience. There's a question from Olaf Optenkamp to Wilfried. He said the computer architecture seems to aim on the ADS to be fail operational due to failure of internal components. 26262 and the SOTIF only, or does it deal with operational safety failure not because of internal system errors, but due to surprising events on the road that the system simply was not designed for? Did you get all of that, Wilfried?
Yes, and I have it in text right before me. It's a very good question, and I think you're quite to the point. I mean, certainly the ISO 26262 and SOTIF, they must be covered by the conceptual architecture. And as you point out, but what with an edge case that you missed in your analysis? And I think there are two answers to that question. First of all, the conceptual architecture must be structured in a manner such that you have a fallback system in place that is capable of operating in almost any operational design domain. So for example, it must understand that it probably doesn't need to understand what specific obstacle there is in front of you, but it probably is sufficient to understand that there is some obstacle, and therefore it's sufficient, or it's a good design choice to brake or to slow down the vehicle. So I think the first answer is to have sufficient fallback systems in place and monitoring systems in place that are less dependent on the actual operating design domain that you are operating in. And then I think really the safe autonomous cars will not just jump into existence everywhere, but they will start in very restricted operational design domains in the first place. So my best guess would be that we start seeing the system on the highway first.
Thanks. Another question is for Missy from Mallory Graydon. what are the main benefits of collaborative driving approach compared with autonomous driving? And I guess by collaborative, it's sort of an L3 question.
Well, I mean, I see collaborative driving as much more than just the proposed L3 level. I think it's any time where you've got a system that helps protect the human from potentially a bad envelope of performance. So, for example, and I give the example in my written response. We see people taking corners to curves of roads too quickly, and they inevitably, they cannot beat the laws of physics. So if we know what road they are on and the car knows the speed, it is a very straightforward computation to say you should not be, the car knows that you should not take that speed greater than whatever the upper limit is, or you're going to go off the roadway. Like, why don't we have that in cars? I do think there's an argument about, if cars know that you're speeding, should you be able to restrict your speed? And I'm not saying that we should have some kind of overarching heavy regulatory hand to limit any kind of speeding. But if we know that some speeding is going to kill you, then why can't we have the system step in and protect you? So Toyota had for a while, and maybe they still have their efforts going on in their Guardian concept. And I'm a big fan of that. Look, let the human and the machine work together. Humans can still resolve issues around bad weather, some unusual situations that you're in, urban environments where potentially pedestrians and bicyclists can pop out from behind obstacles. So I think I would like to see the view move more to one of team as opposed to one of replacement.
Thank you. Ravi, from Mallory Graydon. Machines process information within defined models, sets of variables with understood real-world meanings, so forth. Humans can identify when the model is oversimplifying relevant reality. So far, systems can't. If we're going to build what you describe, wouldn't we have to solve that unsolved problem first?
I think to a point, we are continually evolving to address that problem. The machines are becoming more and more capable, but where we don't do a good job, where the neural network, which is the mainstay, doesn't do a good job, is to handle uncertainty. As I was saying, the advantage of going last is that your colleagues have pointed these things out, and I think perhaps Missy did, or I don't know, one of my colleagues did, is the issue of handling uncertainty and making decisions in face of uncertainty. We are used to having these kinds of environments in our daily life. We handle these kinds of uncertainties. We make decisions. That kind of reasoning, that kind of thought process has not come into the mainstay of artificial intelligence. We're starting to creep in that direction. But until I believe we can bring that kind of thinking, which I think you're also alluding to, we won't be safe in taking the driver completely out of the car. But we could, in the meantime. I'm a great believer in being progressive in this. People are going to be more or less attentive as we provide, as the vendors provide more and more automation. Some are easier to handle than others, and they will slowly become less and less attentive. On the other hand, by the time you take the driver completely out and have Uber taxis and running around in San Francisco as might happen, I think we we need a lot more actionable intelligence to be provided to the vehicle. May not be mimicking the human, but in allowing the vehicle to do the kind of reasoning that we've all been discussing in one form or the other. And that's really the big difference between the safety issues that we face with the vehicles, the autonomous vehicles, and traditional safety issues that we have faced over the years. And that's a big difference.
Thanks, Ravi. Phil, we have a question from Pierre Bluher. I'm not pronouncing it correctly, I'm sure. He asks that your point is true, and I guess the point is, the point you made, I'm not sure what it is. The ISO 26262 is owned by the industry and not by the authorities. Therefore, as laughable as that is, no commitment. Secondly, the way it is written, it is often ambiguous and not at all striving for state of the art. Not sure just what the question is, but
I can comment on that, sure. Okay, so I think what Pierre is pointing out is that ISO 26262 is not as strong as safety standards in some other industries. And it is mostly an industry-driven document and with a lot of industry-requested compromises in it. On the other hand, it is the issued industry safety standard that's been around for more than a decade. And the other industries, rail follows EN 50, 128, 126, 129. Chemical process follows IEC 61508, and so on. These industries, by and large, set their own standards and then follow them. Okay, so while, sure, anyone on the standards committee, and I am on the standards committee for a bunch of different automotive standards, they're all compromises, I get that, but at least it's a baseline. And if the industry can't even follow its own baseline standard that it itself wrote, what the heck is going on? But that's where we are. We don't have companies committing to following their own safety standard. So what I would like to see is exactly what U.S. Department of Transportation proposed back in, I think it was December and January, this past December, January. They said, hey, let's use the existing standards. Everyone should follow 26262. They should follow 21448, safety of the intended function. They should follow ANSI UL 4600, and not in that document, but they should also follow the testing standard J3018. If you follow those standards, you have a baseline for safety and you can improve from there. What we have now is basically a free-for-all. Companies do whatever they want. There's some good actors. There's some actors that are probably not following best practice, and that's an issue. That's a concern, but we don't even know. That's where we are. We don't even know.
Yeah, agreed. A question for Wilfried from Amelia Chirochka. Given the envisioned high-level abstraction of a reference architecture that you discussed, how can we make it applicable on real systems? Could we attach a purpose to such architecture?
Yes, absolutely. I mean, when I speak about a conceptual architecture, what we actually mean is, or an example would be the doer checker with fallback approach. So you would have the doer, the checker, and the fallback as 3 FCUs. And then you would have further FCUs that take care about the distribution of the control signals to the actuators. So that's one possible mapping. One possible mapping in a sense that the doer, the checker, and the fallback, each of the FCUs would be an individual ECU. And then the question is whether you can combine some of these FCUs in single boxes or not. So I think this is where the engineering trade-offs come in. So yes, I think you're quite right. Security needs to be handled and addressed early on because there is no safety without security.
Thanks. Demetria, maybe it's time to take a little break and post the results of the poll.
Yep, can you see them?
Okay. I guess we're not surprised that The majority being answer C. Although I think worldwide only 10% of the automobiles are ADAS equipped, but I think in the US and in certain countries in Europe and Asia, most all of new automobiles have at least one ADAS function. Well, thank you for that. 29, 14, and 63. Thanks. Getting back to our questions. To Phil from Carl Landwehr. Can you comment on the existing regulatory structure for auto safety in the US and Europe, say, and what changes might be required to provide the kind of standards and enforcement that you see necessary? In other words, here's a solution to a problem.
Sure.
You have it.
Sure. In Europe, you generally see a little more prescriptive use of standards and a little bit more rigor in the engineering. So for example, the test in Europe, you need to get permission, whereas in the US, in many states, you just go out on the road and do whatever you want. So in testing, you see Europe taking a much shorter leash on folks. In general, though, all the standards and all the certification are based on vehicle test. So in Europe, you have the homologation approach where all the vehicles have to be tested before they're allowed on the road. In the US, you have the FMVSS, Federal Motor Vehicle Safety Standard approach, but there the companies self-certify and the government just checks up on them. So different strategies there. But in both cases, we've known for decades that if you really want software safety, the way to get software safety is to follow the standards and then use testing to check the standards, not just test the vehicle. A road test for an automated vehicle is going to prove it's not terrible. It's not going to prove it's safe because who knows what's code in there? I mean, maybe Missy's students wrote that code. Who knows? She loves making that joke, so I bring it up. But the reality is, unless you have some experience and unless you have some folks who really know safety, if you just go slam into some code together, you're not going to get a good vehicle no matter which school they went to. That's just you need to follow those procedures. So what I see coming is exactly what US DOT proposed, which is we're going to have this industry follow safety standards, and they're going to have to do it on their own, or when bad things happen, you're going to see increasing regulatory pressure. So it's up to the industry whether they want to get ahead of this or not.
Thanks. Missy, a question that ought we be pushing to skip hands-free and go directly to fully automated?
I agree that if the technology were really there and ready to be deployed operationally, it would be better to skip this in-between state of driver assist. But right now, while it might be better, it's just simply not possible. And I think what we're looking at is how to balance the driver niceties. Like, I mean, we don't need advanced driving assist in terms of lane keeping. We just like it. We do need automated emergency braking. And that's where I think we need to be clear about what technologies. I hear Phil doesn't like L2+, but I think what we need to do is we need to be clear that there's L2 must-haves and there's L2 nice-to-haves, and nobody actually needs autopilot. They just want it, right? Whereas we need some automated tools to keep us from having accidents. So yes, hands-free is bad, but I don't want to throw the baby out with the bathwater and say there are some automated driving assist technologies that are good that we need to keep, and some that we need to keep an eye on.
If I can just add a clarification to Missy. So I don't like L2+ because it's just marketing puffery. But the deeper issue is—
Explain L2+.
Sure thing. So there's the
audience.
There's the infamous SAE levels, where level 2 means that steering and speed are controlled, but the vehicle driver is in charge of handling things the car doesn't see. And the issue with that standard, J3016, different than 3018 I mentioned before, is that it's not a safety standard. It says it's not a safety standard. And all the regulators treat it like it's a safety standard, which is just crazy, right? And so what Missy is saying is, and okay, you can rebut if I get it wrong, but you need to do something that's safe. Just because the standard says you can build it doesn't mean you should be building it.
I think go
ahead, Ravi. Just
as a matter of practicality, we're moving from a situation where we understand the failures. It took us many, many years to understand them, and we work through. Here, when you bring in uncertainty and machine learning methods, and you have a whole range of new problems that we haven't handled, that standard redundancy methods that we use can't address the decision-making that the machine has to make. So it makes sense to me that we move progressively and have these semi-automated environments that we can still handle, we're still supposed to watch over. And I think progressively, perhaps learn to detach and let the machine handle it. Perhaps.
Agreed. Wilfried, question from Robert Stroud. How does your architecture handle diverse inputs when there is no objective source of truth?
Yeah, I mean, good question. I think it boils down to having the do and the checker in particular, having different sensor inputs, for example, potentially coming up with different world models. So I think the question is, how do you handle false positives and false negatives? So certainly you have to ensure that the monitor catches all the dangerous trajectories. So it must never be the case that the doer, the primary ADS, generates a trajectory that would cause the system to go into an unsafe state. So the monitor must be overly pessimistic in that. But that results in potentially false indications of the doer. So this is the open question. There is an open question, of course, how much of the coordination between the doer and the checker are allowed. And there are two camps. Some argue that no coordination must be done. Others say that some level or the entire world model can be exchanged between the doer and the checker. But I think I fully agree. I think that needs further investigation, and it's a clear and very attractive research problem.
Yeah, good. One last question to Ravi from Peter Bishop. He asks, I see two issues here, fault tolerance and functional safety. Functional safety of AI seems like the most difficult one. Have there been human versus AV comparative studies that you're familiar with?
Well, I haven't seen a side-by-side comparative study that is meaningful with controls and so on. On the other hand, there is at least US data and state-by-state data on safety of human drivers. At least in California, there is data on piloted vehicles, meaning with human pilots, but substantially the vehicle is independent until it decides for a variety of reasons that it can't handle, or the pilot decides that they must take over. Okay. So that kind of data exists, but not, I think, precisely in the way that you're talking about.
No, don't want to cut you short. I think we're getting close to the end of our allotted time. Okay, follow-up. If you're interested in continuing today's discussion, we've set up a Slack channel workspace and a mailing list to join. I'll give you a minute or half a minute just to write this down. Unfortunately, you can't click on it. This link will be sent to you in a follow-up email from our IFIP coordinators sometime next week, just in case you cannot write it down quickly. I'll display it again. Up there. Next. So here's the thing. And to wrap things up, sincere thanks to all involved in this, in the organization and participation in this event. Our IFIP coordinators, our panel organizers, our distinguished panelists, and our audience, whose size and active participation were certainly necessary conditions for the success of this panel. I'll turn this now back to Demetria.
Thanks, John. Again, on behalf of the GI and on behalf of the IFIP Events Coordination Committee, thank you very much to the panelists and the organizers. Thank you, John, for your lovely moderation. And thank you especially to all of the participants today. You can see a recording of this talk and learn more about the upcoming events at ifip.org/Jubilee60. Also, make sure you follow IFIP on Twitter and LinkedIn so that you don't miss the exciting events that we have planned for the Jubilee. So thanks again and have a lovely morning or evening, wherever you may be.
Thank you.